It's a pleasure to have here with us Paulina Cabrera Ramírez from the Universidad Técnica Federico Santa María of Chile. And she will be talking about criticality of a hairy black hole solution, how scalar fields modify van der Waals-like phase transition in Reissner-Nördstrom black holes. And Paulina, you're going to have 25 minutes plus 5 minutes of questions, and I'm going to let you know when you only have 5 minutes left. Okay, so at 20 minutes, I'm going to let you know. So without further ado, Paulina, you can start.
Okay, thank you very much for your presentation. And I'm going to talk about phase transitions in extended phase space of two types of black holes. First, I'm going to review similarities between criticality of the Reissner-Nördstrom and the van der Waals, and then I will show our results of how including a scalar field modifies its behavior for a type of hairy black hole. Okay, introducing black hole chemistry. In the mid-70s, with the postulation of the Hawking radiation that allows black holes to emit thermal radiation, and Bekenstein-Hawking entropy, whose second law is related to the black hole non-decreasing area. Black hole thermodynamics was born, and it can be shown that its geometric parameters are related with thermodynamic quantities that satisfy a first law very much like any other non-gravitational thermodynamic system. With the difference and motivation that here is no analogous in the PDB term. However, considering the SMART formula, that is basically scaling arguments applied to thermodynamic functions, where P and B appear naturally here, black hole thermodynamics can be extended consistently with that, with identifying the cosmological constant as a pressure here. And the consistent first law, as it shows here, this is the corresponding first law, and here you can see that the mass in this case acts like an enthalpy in that relation. This is basically the essence of black hole chemistry, named partly after the plethora of complex behavior found in this system, like van der Waals fluid, triple point, and etc. Some of examples that I will show soon. First, we are going to review the criticality of the Reissner-Nördstrom black hole from this extended thermodynamic view. And this is a review based on the work of Kubiznak and Mann. So as usual, we start with the action of Einstein-Maxwell theory, where R is the rich scalar that encodes the curvature, F is the gauge field, and lambda is a negative cosmological constant, from which it follows that the equations of motion are 3 and 4, with the solution of the metric in this form, where M is the mass and Q is the electric charge. The thermodynamic relation in terms of can be computed. Here the thermodynamic relation can be computed in terms of the radius of the black hole. It can be easily calculated in here, and then we're going to work in the extended phase space associating lambda with the cosmological constant, as I mentioned, and the conjugate quantity turns out to be the volume, which is conveniently the sphere of radius the horizon, and the first law is satisfied. For fixed Q, we can find an equation that relates PV and T, the equation of state, and it can be seen graphically in this left picture, and you can see that it looks very similar to the known van der Waals at the right side. In both cases, phase transition can be roughly seen as the oscillations in one of the isotherms, like here. Because for a constant P, there will be many possible values of the volume representing different phases of the system. And the criticality occurs in the limit when phase transition and starting to happen, described mathematically by this condition, where can be shown here the critical point where there is an horizontal line and has concavity 0. Applying
Muchas gracias, pero sabes, doy clase hasta las 3 y a las 4 tengo mi reunión aquí en la de GAPA.
Applying the condition, this condition to this equation, the critical point can be easily obtained for Reissner-Nördstrom and van der Waals, and setting the van der Waals parameters of the theory, A and B, like this. Both systems give the same critical point, and it is also interesting to note that the ratio C is universal for every van der Waals fluid, because it is independent of its parameters in the Reissner-Nördstrom case. It is not only constant, but it is also exactly the same. So here are some of the quantities that correlates both systems among others in extended thermodynamic frame. Now we are going to analyze phase transitions through stability arguments by looking at this free energy plot that I personally find very fascinating, because despite its simplicity, there is a lot of information you can extract from them. The first thing you can see it exhibits the typical swallowtail behavior for phase transition. This that resembles a swallowtail, that's its name. And phase transitions are seen by global stability criteria. It states that the phase preferred by the system is the one that minimizes the free energy. Here, for example, for the same temperature vertical line, this line is stable against this line because this line has less free energy than the above one. Then phase transitions occur if the preferred path varying some parameter. T in this case present a discontinuity in one of in some order of the derivative. Here, for example, this is the path that the system follows, and here is a discontinuity in the first derivative. So here is a phase transition. You can also describe the different phases by looking at the slope. According to this relation, slope is related to the entropy, and the entropy with the area of the black hole. So the steeper is the slope, the bigger is the black hole it represents. So here, decreasing the temperature, there is a transition from large to small black holes. And finally, the second derivative represents local stability. I mean, how the system reacts to a small variation of the thermodynamic variables. For example, this negative concavity shows stability, and that positive one shows that this phase is unstable locally. Both stability criteria are derivable as a direct consequence of the second law. And now let's move to the case with a scalar field, in which I will show our results with Astefanisi, Mann, and Rojas. And we start with exact hairy black hole solution to the Einstein-Maxwell dilaton theory with a non-trivial self-interaction reflected in this potential. And the equations of motion are this, where eta is an integration constant of the theory. And we can see that it's still spherically symmetrical because omega, the conformal parameter, represents this change of coordinates. Note that we are working here with x, that is a dimensionless parameter that runs from 1 to infinity, where the singularity is at infinity, and we have a boundary at x equal 1. Now, the thermodynamics are a bit more complex, but the idea is exactly the same, and we work again in extended phase space. And if we try again to for fixed Q to relate PV and T in one equation, we see that this equation doesn't depend explicit on P, but we can extract the dependency through eta, cleared by the equation of the horizon. So it is not possible to find an analytically equation of state, but we can analyze it parametrically, being x the parameter. So we can plot numerically our results. Doing that, we find 3 distinct regions for different values of Q. For Q less than a Q minimum, there is no criticality here. For an intermediate value of Q, we observe 2 critical points here, and just one of them represents phase transition, as we will see soon in the next slides. And for Q bigger than some Q0, we find a Reissner-Nördstrom-like critical point. Analyzing its free energy, I show first the simplest cases. For small values of Q, no phase transition occur. For the bigger values of Q, we know again this swallowtail behavior and similar phase transition as the charged black holes that represent the large small phase black hole phase transition. Also, it is important to notice that here observe extremal black holes given by the 0 temperature. And last but not least, the intermediate region where the most interesting things happen. For this value of Q, we see the evolution of the free energy in a range covered by this GIF, and we are going to analyze frame by frame what happens. In A, an inverted swallowtail is forming, but is not a critical point because it's not the phase that minimizes F. This is the line that minimizes F. In B, a swallowtail is formed when the arm of the inverted one intersect the left part of F here. We keep increasing the pressure, and the important results appear here. Following the path that minimizes F, this one, T encounters a first order large small phase transition because its first derivative is discontinuous here, and if we keep decreasing T, F takes a discontinuous jump to this original configuration, a zeroth order phase transition. So we find a large, small, large phase transition, and this is called a reentrant phase transition, when the system comes back to this original state after an intermediate phase. In D, the temperature of the two cusps coincide, and the zeroth order phase transition ends.
You have 5 minutes now.
Okay. And then keep decreasing the temperature. We see that here in E, only the first order phase transition survives, increasing P a little bit more, and the normal swallowtail goes down until it intersects the top of F, and the inverted swallowtail disappears. Then the swallowtail is getting smaller and smaller until it disappears at the second critical point here. So in conclusion, allowing variation of the cosmological constant, a strong analogy with the van der Waals fluid appear for charged black holes. In our work, the scalar fields adds more complex criticality behavior, and we find a reentrant phase transition, the first example in 3+1 dimensions in a consistent theory. And here is important to notice that maybe it could be a thing that could be rubbish to vary the cosmological constant, but our results here, those phase transitions are found by it at constant P. So otherwise we couldn't find this amazing behavior. And this result can be useful in the context of AD CFT correspondence. Thank you so much.
Okay, so let's thank Paulina for the nice talk. And are there any questions? We have a few minutes for questions. Okay, so I see one raised hand. Peter, you can go.
Hi, Paulina. One question. Maybe you don't know, but can you go back to the model you have solved? You had the action and the potential for the scalar field. Great. Yes, that one. Do you have maybe you don't know, but do you have an idea of what that profile looks like? I mean, you put a potential for the scalar field, and you were able to solve it exactly. So this is just like a fit. But do you have any idea on why that potential in particular, or could you have deformed it a little bit, or is there an intuition you could tell me about this? Why that potential in particular, besides the fact that you can exactly solve the equation?
And actually this is a particular case of a more general theory with in which these solutions here, the an Avalon and et al. Found are